Just sticking with the same schedule, just recording this 2 minutes. So now we'll have Justin give his second talk on singlet fission.
Okay, thanks. Thanks to you who stayed after the first part. Just scared away too much. Yeah, the second part is a little bit more practical, some more experimental results and some experimental techniques that we've used and other people have used to try to detect, characterize singlet fission. Some of the slides I meant to make a little nicer, especially toward the end, so it'll be a little rough, but we can go through it anyway. So the agenda for this part of the talk is to discuss some ways of detecting and quantifying triplet formation. So this is something that not everybody, even spectroscopists, not everybody works with on a daily basis. So it's useful, I think, for people to know how you go about detecting states like triplets that don't have absorption from the ground state usually. I'll talk about some experimental work that we've done on dimer systems, experimental work we've done on solid systems, and then hopefully you get a chance to look at some singlet fission devices or devices that take advantage of singlet fission, mostly from other people in the field, not from our own work. So detecting and quantifying singlet fission. So first thing that people often say is, well, why don't you just look for phosphorescence? Phosphorescence is this spin-forbidden radiant of decay from a triplet state. So it's spin forbidden because you need to split the triplet spin in order for it to go back to the singlet ground state. And in some molecules, phosphorescence is quite bright, but most of those molecules, here's a case where it's the yield is in the 80–90%. But all these molecules contain heavy atoms, iridium, and others, things like that. Most hydrocarbons, things that just contain carbon and hydrogen, or even sometimes oxygen or nitrogen, most of them do not phosphoresce, especially at room temperature. You may be able to cool them down to a few degrees Kelvin or something, and then you might see some emission from the triplet state. But generally speaking, you're not going to see emission. If we were, it would be kind of a nice way to quantify it. You could just measure the quantum yield of phosphorescence, and for example, if it went above 100%, then you would, the only mechanism that would allow for that to happen would be singlet fission. But unfortunately, most systems that's not available as a technique. Another way would be to use the same kind of technique that's used in multiple exciton generation, or essentially a kinetic determination. And in that situation, people use pump probe spectroscopy and measure the Auger recombination amplitude and time in nanocrystals by changing the pump intensity. So increasing the pump intensity, you generate bi and tri-excitons, you watch them decay in the bleach, and you get a rate and you get essentially a yield. And you turn down the photon intensity, you see the same decay pathway. You can measure the amplitude and get a yield of the multi-exciton generation process. So that's potentially useful in singlet fission as well. And I already discussed the reverse process of singlet fission and how it's analogous to multiple exciton generation, or how it's analogous to Auger recombination. It would also require, though, that you see fluorescence. And fluorescence from the singlet state, of course, is certainly possible, but not in all situations will you expect to see this. For one example is if you have designed your molecule in such a way that the threshold, the 2 times the triplet energy is below the singlet, and going this way is uphill energetically, you will be inhibited, and so your fluorescence will just decay and you won't see an additional component. And again, not all molecules even fluoresce very strongly from the singlet state, and so it wouldn't necessarily be a quantitative measure. People have tried to use this and somewhat successfully in the past. This is a paper from Chris Bardeen. He used Pentacene dimers. And what he did is he looked at the monomer, just taking this part of the molecule, looked at its decay in solution, and got this dash curve here, or this blue curve here. When he put the dimers in solution and made them very dilute, so that there's no chance that they're close enough to each other that they could actually collide, and that one triplet here could collide with one triplet there, produce a singlet. When he made it very dilute and turned the pump intensity down, he did see a bi-exponential decay of the fluorescence. And so he interpreted that as this is the initial decay of the singlet, and this is delayed fluorescence, because it occurs on a much longer time scale, because the triplet lives much longer than the singlet does. And you could kind of get I would say, a semi-quantitative estimate of the yield in these Pentacene dimers. He found it to be a few percent. Most of the systems that we've looked at, we've tried to design them such that this situation, it happens where you cannot go, or it's inhibited to go back uphill to the singlet state and fluoresce. So most of our systems will not work. Tetracene is a case where 2 times T1 is actually just a little bit above S1, and so going back and forth is readily allowed. Another situation that's difficult, makes this difficult, is in crystals. Lots of times you can make 2 triplets maybe close to each other, but in a short amount of time, they diffuse away from each other. And so before the annihilation process happens, all of a sudden you've got triplets that are far away from each other. And so you don't expect then to see fluorescence from that state. And this is kind of, in a way, I guess, similar to the case of strongly coupled quantum dot films for MEG. The Auger recombination time gets longer and longer as you make them more and more strongly coupled, because you're removing charges away from each other and not allowing them to undergo Auger recombination. So it's at some point that becomes difficult to use in highly coupled quantum dot films also. So another possible way to do this is a kind of a very simple way and very old way, and that's comparing with a standard. So this could also be called relative actinometry, using some older language. And there's a group at the radiation lab at Northwestern that used to spend a lot of time tabulating extinction coefficients for triplet absorption and quantum yields and things like that in different solutions, and trying to develop a big table of standards that anyone could use. You would put a standard in solution to measure the triplet absorption, knowing the extinction coefficient, then you could compare it with your own molecule and just basically take a ratio. You would get a triplet yield in that way. This is a table you see even within some of these rows here. There's quite a bit of disagreement with just one molecule in different solvents, and even in the same solvent, there's quite a bit of spread. It's difficult to measure extinction coefficients in general, but for triplets it's even more difficult because you have to be very careful that you don't, like oxygen often quenches triplet states, so if any oxygen is in the solution, the lifetime will be shorter and you'll get an inaccurate measurement of the extinction coefficient. There are a lot of corrections that go into these. So sometimes these are useful. We often use anthracene as a pretty good standard. We often use that as a standard, but it's not always practical. And a lot of these just absorb in the UV, not in the visible, so often that's not practical to be able to tune your laser system to the UV and then back to the visible and expect to have a decent comparison. So the way that we've used most often for molecules in solution is to do energy transfer from a sensitizer. So a sensitizer is a molecule like anthracene, for example, that forms triplets with a very high yield. It would be ideal if it were 1. It's not in anthracene, it's on the order of 80%. But if it were 1, that would be ideal. The idea is that you excite anthracene just alone in solution. You measure its triplet-to-triplet absorption. Remember, you can't measure, most often, you can't measure S0 to T1, it's ground state absorption. But you can measure spin-allowed transition of T1 to some higher line T. So Tn is just usually what we say. So that's what this absorption is here. So we measure that. We measure the lifetime. It's usually long, 50 to 100 microseconds. Triplets live a long time typically. And then we add our target molecule, so let's say a dimer of this diphenylisobenzofuran, to the solution. We still try to just preferentially excite the anthracene, and then we watch the triplet energy transfer from anthracene to our molecule. And we can kind of do that in a spectroscopy experiment. So initially we see only anthracene absorbing, or mostly anthracene, and over time the anthracene goes away and the triplet-to-triplet absorption of the diphenylisobenzofuran grows in. You can see that from kinetic traces. It's the anthracene triplet gets short, and the diphenylisobenzofuran triplet rises, and of course it decays on some very long time scale. And then the final step in this process is to take away the sensitizer. Just put your molecule in solution and excite it directly using essentially the same number of photons in both cases absorbed. And again, we see the same triplet peak, and we measure its amplitude relative to the final amplitude that we measure here. If we know the initial triplet yield of the anthracene, then it's just the triplet yield of our target compound is just a ratio multiplied by that triplet yield. The nice thing about this is we don't have to know the extinction coefficient for anthracene. We don't have to know it for our compound either, because we're comparing 2 spectra that are identical. So we're not comparing 2 different parts of the spectrum, just 2 spectra exactly the same way, like what is the amplitude. So that's very nice. We do have to rely on relatively accurate measurements of the anthracene triplet yield, but if it's very high, if it's close to 1, then our error will be quite small. So this is the way that we've done this pretty often. Crystals, it's harder because you can't rely necessarily on energy transfer from a sensitizer in a crystal. Maybe you can dope the sensitizer into a crystal and hope to excite it directly, but often that energy doesn't make it where you want it to go. It's simpler in solution, but more difficult in crystals. So I try to illustrate here schematically what, this is one thing I didn't quite do, this is time on this axis. Schematically what you'd expect in a crystal system with and without singlet fission. So this is an experiment you're doing, it's a pump probe experiment, you're looking at the change in essentially the photoinduced absorption from your sample. So initially you excite the sample, this is also the photoinduced absorption, but we're looking at the S0 to S1 transition. So initially you excite the sample, excite the sample, no triplets form, no singlet fission, your triplet absorption stays at 0. But your bleach, which is essentially the S0 to S1, the loss of S0 to S1 oscillator strength, your bleach decreases because as soon as you put an excitation there, this part of the molecule will no longer absorb light at that same wavelength as strongly as it did before. And so that's why you see a loss in that transition. And that happens along with the laser pulse and then decays along with the relaxation dynamics of the crystal. So if you have singlet fission in the crystal, you excite with one photon, you initially form a singlet state, so you still have the same situation. Initially no triplet, and initially a large bleach component. Over time, if singlet fission happens, then you have these two excitations that live across at least two molecules. And so there's a change. So you see the kinetics, the rise of the triplet here, so let's say it's a picosecond or nanosecond time scale. And you also see the additional rise of the bleach component. And the reason you see additional rise of the bleach is that you've gone from essentially blocking one molecule from absorbing to blocking two molecules from absorbing. And so you see an initial rise in the bleach and a secondary rise. So calculating the triplet quantobule in a crystal then just boils down to finding out what the final absorption strength of the triplet was here after all the triplets have formed, and comparing that to the initial bleach strength. So this is essentially how many molecules did I initially excite, and this is how many molecules ended up with the triplet on them. And so the ratio of those two things multiplied by the extinction coefficients is the triplet yield. So in this case, you can see this is maybe 1.5 times bigger than this, and if the extinction coefficients were the same, then the triplet yield would be 150%. One additional way of detecting the influence of singlet fission is this secondary rise that I mentioned. And if you measure the amplitude of the bleach of that secondary rise and compare it to the initial rise, that's also a measure. So let's say it increased 50% from where it was initially. That would mean that 50% of these molecules underwent singlet fission. Again, you'd get 150% quantity. So I'm going to show some actual experimental results for dimers and for crystals. Again, it's mostly from this system that I mentioned earlier. It's a good model system. It has the right energetics, and we've studied it a lot, so we know it well. So we tend to go back to it time and again. And so we studied the molecule, just the monomer itself, isolated in solution. Calculations and spectroscopy gave us an idea for where all the excited states are. And so now we can go look at dimers and know where to look for some of these triplet absorptions. And so we started with what we would call weakly coupled diphenyl isolipids if you're in dimers. And by that I mean they're certainly tied together covalently, as you can see, but they don't have a lot of strong interaction with each other. And you can tell that by looking at the absorption spectra. So this is the absorption spectrum of the monomer, and this is of these two dimers. The shapes themselves are almost identical. The positions, there's no large shift. So the two molecules are essentially acting as independent halves of a dimer. And the other way that you can tell is that the extinction coefficient, which sort of measures the probability of absorbing a photon, doubles when you go from one molecule to two. Of course, that makes sense. It should double because you have twice the probability of absorbing a photon if you've got a molecule with two identical chromophores. If these were strongly coupled, you expect a big shift in the absorption. Maybe the extinction coefficient wouldn't be exactly double. So we're pretty confident these are just weakly coupled dimers. So we know where the triplet absorptions are. And if we measure, this is from the monomer. The monomer doesn't form any triplets in solution by itself. It just fluoresces, no triplets. This is the spectrum of it though when we sensitize it, so we know where that is. The dimers themselves do form triplets in solution, without a sensitizer. So they're undergoing some mechanism of triplet formation. And we can see that because the dark lines here are without a sensitizer, and the spectrum looks essentially identical. The yields are quite low, however. And so it's not necessarily clear immediately that if the yields were above 100%, we would say, okay, this is great, single fission is occurring, and we know that it is. But with the yields less than 20%, it's a little more difficult to prove that it's happening. But one of the possibilities in these weakly coupled dimers is that we are undergoing singlet fission, but through two successive charge transfers. So this indirect mechanism, we form a real cation anion intermediate state. And I showed some evidence of that before, and I'll just show it again. So for these weakly coupled dimers, we see after excitation, we see a slow picosecond formation of an intermediate state. As that decays, the triplet rises, and they rise with the same time constant. So the idea is that we're going from here to here, and then from here to here. I'm sweeping under the rug a lot of details that may suggest that this isn't what's happening. But it's one of several possibilities that we're sort of toying with and trying to prove. When you go to a more strongly coupled dimer, it may not be clear. I showed these structures. I guess I didn't really explain the structures very well. This structure is similar, probably noticed, it's very similar to this structure. The only difference here is that there are methyl groups on these positions in this dimer versus this dimer. So you might say, well, why are you calling one weakly coupled and one strongly coupled? Those methyl groups cause the two halves of the dimer to twist. And so you don't have, whereas in the other case you have one monomer and then a twisted monomer. They don't interact strongly. In this case, there's nothing preventing those two molecules from being in a plane, which means that essentially you can have conjugation through the entire molecule. And so sort of particle in a box idea, again, you've made the length of your box effectively a lot bigger. And so this is a little hard to see, but for this molecule, the absorption is in purple. On this scale, it doesn't look like much of a shift, but it's actually quite a significant shift, and the emission is quite different. So that, initially we thought, well, that could be a good thing. With the weakly coupled dimers, less than 20% triplet yield, that's not very good. Maybe we just need to couple them more strongly together, get some of those matrix elements to be bigger. That would be the right thing to do. So initially this seemed like a good idea. However, we noticed something about the triplet formation process that caused us to say, well, maybe this isn't the right thing to do. If you look at the what's called the action spectrum of triplet formation, essentially it's sitting on a peak of the triplet absorption, measuring the triplet quantum yield as a function of the wavelength that you're scanning over. And then you compare that to the absorption spectrum. So for the weakly coupled dimers, the action spectrum and the absorption spectrum look identical. The triplet yield doesn't matter. It doesn't matter where you excite the molecule, you get the same triplet yield. But in a strongly coupled dimer, you notice the absorption, which is here, and the action spectrum are shifted from each other by a significant amount. We're calling that an activation energy. So you can't just excite the molecule at its lowest position of absorption and get any triplets out of it. You have to excite it much higher. And essentially what seems to be happening here is that we've pushed the lowest excited state, S1, down because we made this box so much bigger. But we've left the triplet essentially in the same place. And so 2 times the triplet now, instead of being about the same as S1, is now considerably above S1. And so for singlet fission to occur, you need more energy than just S0 to S1. You need this much more energy. And that's not an optimal situation. That's bringing us closer to this, the first case I mentioned with smaller exchange splitting. And the yields in this case are quite small. They're just a few %. So it suggests that even though you put in enough energy up here for singlet fission to occur, the relaxation processes that bring it back to S1 are easily outcompeting singlet fission. So that's not necessarily the best case. So we have 2 weak, we had 2 strong. What might be just right? We're working on that now, and these are examples of what I might call intermediate coupling in these dimers. And I threw up a couple of singlet fission yield or a couple of triplet yields here. They're not fantastic, but it's sort of preliminary. What's interesting about this series of dimers is that again, you look at them, they look very, very similar. They all have the same, actually they all have the same chemical formula, right? But they're differing in the way that they connect to each other. So this was the strongly coupled dimer I mentioned a minute ago. We call this a para-para linkage, so para on both phenolutes. And then we have a meta-para linkage and a meta-meta linkage. So you can imagine that here, if electrons want to delocalize, they hardly have to bend at all to go through the entire length of the molecule. Here, they have to bend essentially just once to go through, and here they have to bend twice. And so this molecule is the most weakly coupled, this is intermediate, and this is the most strongly coupled. And we've done a series of measurements, and it turns out this one is the best of the three. It's still not very good, but it's the best of the three. So we're kind of trying to compile as much data as we can, as much intuition as we can, to understand if maybe there's something about this molecule that will never make it work. Maybe there's something about linear linkages like this that will never make it work. But we need some insight into how dimers work. So here we go again. Another question. Sorry, let me start this and then I'll put it back up. Shut it down here. Okay, so the bleach signal corresponds to. Oh, so this is why I probably should have looked at my slides, expecting to give it tomorrow. None of these answers are right. So it's a good question, but it's a bunch of answers from the previous talk. So if you already answered them, I don't know what you could answer. So we'll go back to the slide. Sorry about that. Okay, so I talked about dimers in some of the initial observations that we've made on a model system. But so far it hasn't been tremendously successful. And so someone had asked the question, what about, you study other things besides solution? And yes, we study this interaction in crystals as well. And there's a lot of history, people manipulating the structures of crystals to try to alter the intermolecular coupling. And it goes back many years. This is an example. Parylene is a common example where it has two different forms. And the two different forms have different morphologies. Sometimes the molecules stack with each other very well, and sometimes they're canted at a significant angle with respect to each other. So just relying on the natural, what we call polymorphs of a crystal, the different ways that the molecule likes to make crystals, is one way that we can induce different types of intermolecular interactions. Another way is to change the molecule, and that would potentially change the way it wants to pack. So Pentacene likes to pack in what we call a herringbone pattern. And almost every time you do it, you get a herringbone pattern. But if you put some side groups on it, some sort of bulky side groups on it, all of a sudden now it will pack in a more of a brickwork or face-to-face pie stacking kind of pattern. So you haven't really changed the molecule that much. The core is really the same, but you've changed the way that the molecules interact in the crystal. And so this is the second way of doing it. The third way is a little bit more complicated, and this is some work that I did with Niels Damerower on campus, where we're altering the intermolecular geometries in a dynamic way. So we're using shaped laser pulses to excite specific intermolecular modes in a crystal. So twisting them, moving them closer and farther apart from each other, to try to induce singlet fission at some sort of turning point in a molecular motion. Again, it's a little more complicated and a little beyond the scope of the talk that I'm doing right now. So I'll stick with the static methods of inducing different types of intermolecular coupling. So the first thing that we did was we determined this crystal structure of this diphenyl isobenzofurane. And if you look closely, you'll notice that it forms these stacks. So these nice pi stack systems, and the nice columns of these pi stacks. And all the molecules have a particular conformation of those two phenyl groups. They both twist in opposite directions. All the molecules in the crystal look like that. And the separation is relatively close. So it's not that easy to do spectroscopic experiments on single crystals of organic molecules, because often they're hard to control the thickness, and if they're very thick or full of defects, often the experiment's difficult. So what we do is we deposit polycrystalline thin films using what's called thermal evaporation. So we put powder of the compound in a boat, we heat it up under vacuum. It vaporizes deposits in a nice, thin, and uniform way on different substrates. So this is how we make films to study by spectroscopy. And so the first thing we did was we looked at the films by X-ray diffraction. So we knew already what the pattern should look like for the powder based on what we had determined from the bulk crystal spectrum. And if we look at the one strong peak that we get compared to the bulk or compared to the powder, we realize that our films are highly oriented. So we're not getting all these peaks, so we don't have randomly oriented crystallites all over our substrate. We have highly oriented crystallites, and we're just seeing the reflection from one crystal face, and we can identify which one it is by comparison. So we go in and model this, and we can know that this plane that I've drawn in red here is essentially the substrate plane, because that's the only peak that we're getting in the X-ray diffraction spectrum. So now we have a really good idea of what our molecules look like with respect to the substrate. Now we do most of our experiments, of course, with the substrate normal to the incoming beam, whether it's a lamp or a laser beam. That's just the traditional way of doing things. But if you look at the absorption spectrum, that leads to kind of an interesting phenomenon. So in solution, or in the dilute glass, the blue curve here, this is the absorption spectrum of the molecule. It has three really strong peaks. And we know from calculations what those peaks are due to. The transition dipoles are along Y for these two peaks, this direction. And they're along Z for this strong peak. But when we take the film and take the absorption spectrum at normal incidence, we don't see exactly the same thing. We see the lowest, I've normalized these so that the lowest peak is the same intensity, but the other two peaks are much, much lower, especially this one. Actually, the second peak is reasonably the same, but this one is very different, much, much lower than in solution. And the reason for that is that transition is oriented along this axis of the molecule. So in solution, it doesn't matter which axis of the molecule the transition is oriented. You see them all with the same equal weighting because the molecules are tumbling around, they're isotropically oriented. So you see X, Y, and Z all with 1/3 weighting. But in a crystal, if it's oriented like this, and this is the Z-axis, and all the molecules have their Z-axis along this axis, which is coincident with the laser coming in with a lamp, we're not going to see those transitions at all because the polarization is in this plane, and so it's not going to excite something that has a dipole in this plane. And so that's why we see the loss in intensity here. What we can do is we can tilt the sample. You can imagine if we tilt the sample, we can start to see some of those Z-oriented transitions because they'll tilt with respect to the laser. And so we notice that as we tilt the sample, we lose some intensity in these two, and we gain intensity in this Z-oriented transition. So that's going to become useful in a moment here. The triplet-to-triplet absorption has the same complications. So in solution, we know what the triplet absorption looks like. It's this blue curve, but again, that's equal weighting of all the X, Y, and Z transition dipoles for T1 to Tn. The crystal is oriented, and so calculations were done to say that in this region, it's not just Y-oriented transitions that contribute, there's also a Z-oriented transition there as well. And so if we look at the film, this black curve here, it looks pretty similar through most of the spectrum, but then there's a big chunk taken out of it here. And that chunk is the Z-oriented transition that we're just not seeing in the film at normal incidence. And so this becomes complicated. So in order to actually arrive at a triplet quantum yield, we need to know exactly what the amplitude of the triplet absorption is and how much of it is due to Y and how much of it is due to Z-oriented transitions. And so again, we do this tilting experiment. And this is done, so we're using transient absorption to watch these transitions, and we're tilting the sample and measuring how much does this spectrum change as we tilt the sample. And so going through some math means we get a correction factor for the amplitude that we measure compared to that of bleach. And the correction factor gives us then the triplet quantum yield. And the triplet quantum yield in this system, these thin films, was nearly 200%. And that was at a slightly lower temperature, but it stays above 100% throughout all of the temperature range. There's pretty significant error bars because a lot of these experiments, you have to go through a lot of repetitions, and a lot of times the signal is not that strong. So the error bars are quite large, but in any case, we're confident that this is above 100%. So you can say, almost certainly that's singlet fission happening in the crystal, even though it didn't happen in dimers in solution. So this is a pretty interesting result, and you can examine the kinetics and get some further information. So this is the kinetics of that T1 to Tn, and it's rising on a 2 and a 25 picosecond time scale. So that's fast, but that's not ultra fast, we would say. And if you examine the bleach, so this is the raw bleach signal. It has some little wiggles here at early time, but if you correct for some of those wiggles, here's what it looks like. So it rises fast when you first excite the crystal with photons and create singlet excited states. And then it continues to increase on the same time scale that the triplets increase. And it increases about 80%. And so that leads us to about 180% quantum yield, which is almost exactly what we measured if we just measure this amplitude compared to the initial bleach amplitude. So the kinetics tell us the same story, that singlet fission is happening. It's not really fast, but it's competitive with any other mechanism, so it's essentially the only thing that's happening. This may be a slightly, I did actually finish this question, it looks like anyway. It's maybe a slightly complicated question. I think I'm going to skip it for now because I know I don't have a ton of time. So this diphenyl isobenzopyran, it's a model system. It doesn't absorb very much visible light. It absorbs in the blue, but it doesn't absorb in the red or the infrared. And it's not particularly stable. So we have to do almost all of our experiments with samples that are prepared in the glove box or in some sort of inert atmosphere. And it's not ideal, obviously. So we make a solar cell out of it. Having to seal it in an atmosphere is not ideal either. So we're looking for compounds that are more stable. And this is one of them that we looked at recently. So indigo, probably all of you have heard one time or another about indigo. It's the dye in blue jeans. Very stable, very robust, and very strongly absorbing compound. If you remember from previous talk when I showed that slide about biradicals, I showed a biradical that actually was indigo. It was just twisted. So when it's twisted, you can have these it's a dot-dot resonance structure of indigo. So twisted indigo. And so we already know that it has a significant amount of this biradical character. And so we expect that the triplet energy is going to be really low. And these are some calculations that show that it is really low with respect to the triplet. It's in the right energy range. Indigo has some issues with it that we don't necessarily like, so we've settled on a derivative of it that's called Singlet-triplet. It has roughly the same energetics, it just has a lot longer excited state lifetime, so it fluoresces really brightly in solution. So that's one compound that we've been looking at, and so far the results are pretty promising for singlet fission occurring. Again, we have to go through kind of the same set of experiments that we did with the other compound. We want to look at the interactions between these indigo-like derivatives in a crystal, because we think that the pi stacking is probably the best geometry for singlet fission to occur. So we've made different crystal polymorph in films of the Singlet-triplet, this indigo derivative, and found that they're significantly different. So both in the separation of the molecules, here much smaller, here much larger separation, and also in the way that these phenyl groups twist. So all of that, and also in terms of the amount that this molecule is slipped in this direction with respect to this molecule. So all of those things are important. We're kind of processing that information now. There's one school of thought that says, why go through all of the work to make crystals, characterize them, figure out all these correction factors when you do these experiments, when you don't really need crystals. You just need molecules that interact with each other in some way, but it doesn't have to be perfect. So this is from the Mark Thompson and Steve Bradforth group at USC. They published this paper recently, which is pretty interesting. They took a tetracene derivative, diphenyl tetracene, and they evaporated thin films in the same way that we did. But they found that they could find conditions where instead of forming nice crystalline, polycrystalline thin films, they made amorphous thin films. At least amorphous by X-ray diffraction and any other methods that they could find. Absorption spectra look just like the monomer, so they're saying these are amorphous. But yet, when they measured the transient spectroscopy, they found high yield of triplets, around 140%. All the kinetics matched with singlet fission. So this was kind of an interesting result, and it made us think twice about some of our studies, because they're saying that there's no order, no long-range order in these systems yet. There must be dimer-like, at least dimer-like interactions within the film somewhere that allows for single fission to occur. If it's completely amorphous, then the molecules would be not interacting with each other really. And so this is another way that people are thinking about it. They think that there are certain parts of the film where the dimer-like interactions are just right, and if you excite that part of the film, you get single fission to occur quickly in this way. But if you excite somewhere where the interactions are not right, that's still okay. You create an excitation, it migrates around in the crystal, and eventually finds one of those spots, one of those sort of hot spots, and produces triplets here on a little bit longer time scale. So that's the rationale behind that methodology for making amorphous films. So this is the last part of my talk, and it's not completely finished, but we'll go through it anyway. There's several different ways that you could imagine making devices that utilize singlet fission. So I mentioned one earlier, and Bruce asked a question about making just a Gretzel or dye-sensitized solar cell. So you can imagine doing that with dimers. You can make dimers, attach them covalently to TiO2, and hope to get two triplets injected into the substrate. You can make nanoparticles. If they're small enough, maybe they'll undergo that really efficient singlet fission just like the crystals did that I showed a minute ago. But if they're not too big, maybe the charges will still get out and get injected into TiO2. Aggregates is another possibility. So we have been considering this for quite a while. We have some initial results on this system. Other people have looked more intensively at bilayer systems. And this is a conceptually maybe less complicated way of trying to utilize single fission in a device. So they make the devices in a sort of similar way that you might make quantum dot solar cells. You put a layer, an acceptor, often in C60 or some fullerene derivative, and they just put a thin layer of Pentacene. Pentacene, this is tetracene. People have done tetracene and Pentacene. Essentially, what happens is mostly you excite the Pentacene, and undergo single fission, and they haven't shown the triplet energy level here, but it's somewhere right about where the C60 LUMO is. It injects triplets with, apparently, it's been reported, very high yield, 200%, compared incoming photons to number of triplets being collected. And then the rest of it works like a normal solar cell. So there have been some promising results. The efficiencies themselves are not extremely high, but that's probably because the materials used are not optimal. The vanadiums are not optimal. But there's been some demonstration that the triplets produced by single fission actually are contributing to the photocurrent. Bulk heterojunction is another way. It hasn't really been explored in as much detail, maybe partially because it's a slightly more complicated route. But you could imagine replacing the ordinary polymer that people use with a polymer of a molecule that might undergo single fission, and you get two very long-lived triplets that could diffuse their way into an interface and inject charge. This is just a little more detail on that result that I mentioned a second ago. So you can produce 2 times the photocurrent. So let's say single fission doesn't occur. You just excite singlets and singlets inject. And you get some photocurrent, 5 milliamps per square centimeter. Then you turn singlet fission on, and if the triplet level is here, and you can separate those triplet excitons, and you get 2 times the photocurrent than you would have gotten if single fission had not occurred. But this situation doesn't necessarily break the Shockley quasar limit because, of course, you could also get the same photocurrent if you just had, or you could get a high photocurrent if you just had a lower band gap material. So this is an interesting way of showing that single fission occurs, but it's not necessarily a route to really high efficiency solar cells. That route might require an additional layer, and a layer that not only undergoes single fission, but a second layer that absorbs that red and infrared part of the spectrum. And so people have been playing around with this now for the last couple of years. There's one paper where they combine the sulfide nanocrystals, which of course are strong absorbers in the near-infrared part of the spectrum, and Pentacene, which is a strong absorber in the visible part, and their IPCE, or EQE spectrum here shows that indeed Pentacene is contributing to the photocurrent. It's not just lead sulfide. And they did some calculations to suggest, maybe not prove, that single fission is happening, triplets are being separated at this interface, and that single fission is actually boosting the efficiency. These devices are real low, I think they're 1 or 2%. But there were some more recent reports, not published, that said they were getting much higher, and they were proving to themselves that they were getting EQE above 100%, strictly due to the Pentacene single fission. So this is ongoing work. It's pretty exciting. I think that people are able to so quickly take something that's not well understood and sort of demonstrate it in a device-like configuration. But there's a lot of work to be done. This will probably be my last slide. This is going back to the dye-sensitized solar cell, and how would you design a system that would take advantage of single fission in just an ordinary dye-sensitized solar cell. And as Bruce mentioned, it's complicated. So we would hope that the time for single fission is fast. We can make it less than 10 picoseconds, hopefully even faster than that. The triplets themselves should live for quite a long time, much longer than a nanosecond. So they'll sit there, after they form, they'll sit there and wait for something to happen. And so if we can inject them with just the right time scale, so between 10 picoseconds and 100 nanoseconds, of course avoiding the initial singlet injection, then we should have a very high yield of injection. And so the nice thing about triplets is you have this really big kinetic window to work with. So we can use spacers, bringing these farther and farther away from the TiO2, so that we can tune this time scale to almost anything that we want it to be. But there are some additional complications. So once you can imagine, let's say you inject an electron from this molecule into the substrate. Well, you've got a leftover hole, and then you've got a triplet. So this process of exciton hole annihilation is known to be quite fast. And so there's a chance that you might inject one electron but never inject the second one, because these two would annihilate each other. And so you have to then think about, well, can we come up with a system that extracts that hole away from the substrate faster than the annihilation? And there are ways of doing this. People think about this stuff all the time for dye-sensitized solar cells. So none of these things is a complete barrier, but it does add some complication. So I'll finish here. I think I meant to put a lot more on this slide. But the challenges for single fission are, first of all, to understand the mechanism. And that's what some of those fundamental studies are aimed at. They may seem, some of them may seem unnecessary at times, because unnecessary level of detail to go into if you just want to use this in a device. But I think that understanding the mechanism guides you to what molecules actually will work, and then subsequently what devices will actually work. So controlling the intermolecular geometries is key. I showed you these dimers a lot where it looks like, oh, they're just flat and plain like that, and they just always sit like that. They don't. They move a lot. They have different conformations. Dimers especially are problematic. You want to constrain them as much as possible. And that's where crystals often have an advantage. And as I already mentioned, building on that, you can imagine making devices that actually do take advantage of this process. So at this point I'll stop. Thanks a lot, and we'll answer any questions.
So two questions. Has the 1,3 diphenyl isobenzofuran been deposited on ITO and looked at before, or no?
Oh, it's been deposited on TiO2.
Okay.
And yeah, it injects electrons, shows a good photocurrent. Everything looks great. We just don't know whether those electrons that got injected were singlets or triplets.
Okay. And also, have you ever tried spin coating this material? I know that it's probably not very stable in air, but have any times ever been prepared to be a spin coating?
We have. I mean, generally the quality of the films is lower. The thermal evaporation round gives you the highest quality films. Yeah. Spin coating is second, drop casting is third. So we mostly have stuck with what gives us the best films.
You showed a plot of one of your materials of the yield versus temperature, and kind of showed a maximum there, which, correct me if I'm wrong, but earlier you were talking about at lower temperatures it should get better, and I expected that to continue getting better at lower temperatures. Is there a reason why it reaches the maximum? What's the competing reaction there that's happening? Why is that?
Yeah, it's actually a little bit complex. So in some cases you might expect that the yield would get better as you raise the temperature if there is a small activation barrier. So 2 times triplet is a little bit higher. Yep. So there is some evidence that happens from low temperature to maybe 100 Kelvin or so. It actually goes up a little bit. Why it turns around and goes down is more difficult to explain. There are other things that can happen in a crystal that can also be thermally activated. So just separating charges is one thing, forming excimers is another thing. So adding that additional thermal energy, while it helps single fission a little bit, it might help another process a lot. And and that causes the turnover. We're still working on figuring that out. Is there another question? Okay.
All right, well, let's thank Justin again. We'll take a short break now.